Hi guys, so this video clip is a continuation from the past video clip that I made on iris recognition system. So now is the time to look at the demo. So here, as you can see, I have developed three MATLAB figures. So one of them basically shows how the iris recognition system model is implemented, and one of them show how particularly localization is done, and the last one is showing that how two iris templates are compared, and on the basis of the Hamming distance computed, it will be giving you a decision whether these two iris templates are similar or not. So let's start with the iris system model first. So as you can see, this is the interface. So first we'll insert your eye image. Basically I have two subject eye image named as EEL1 and Briner1. Now you will detect the iris, which is basically your segmentation process, and now after that you can see how normalization is done. So this will be the image after you will do the normalization. After normalization, feature encoding is done to create your iris template, which looks like this. Now let's go to the second figure. Which is showing how localization is done step by step by using the Huffman transform method and the Dogman integral differential operator that I discussed in the previous slide, in the previous video clip. So here you will load your image. So this was the second subject, Brian 1. So now you can see your localized image, which takes this amount of time. Then you remember the trade-off that I mentioned in my previous video clip between the Dogman operator and the Huffman method, that in the Huffman method the algorithm is very time efficient, but it may not provide you the good segmentation result, while in the Dogman operator it's not very time efficient. It takes a lot of time, but it does provide you good segmentation results. So let's see how much time does it take. So it has taken a lot of time actually. So you can see it's taking 13 seconds for doing that localization process. And now let's take a look at Huffman method. See, it's very time efficient. It just takes 0.76 seconds, and these are the bit codes that were used by Huffman method to detect these circles. Now let's take a look at the third GUI, which is used for comparing two templates. So here you insert your images. So these are the images for subject 1, EEL1. I want to take this one, let's say, and now take the second image. Let's try from the right. I'll take this one. So basically these two images are of the same human being, but of one is of left eye and one is of right eye, so the iris pattern should not match. Let's see. This is the template for this, and the template for this is this. So you can see here Hamming distance is computed as more than 0.2, which was the observation which I showed in my presentation also, that these templates are not from the same eye. And let's see some other observations in case where the templates are from the same eye. This time let us take this one. See, so these were the left images of that particular subject, but they were the two different images. And here you can see Hamming distance which was computed is below 0.2, which is the minimum threshold while I did this implementation. So templates are from the same eye. Let's take a look at another observation in which you might have different templates. This time I want to take, let's see, this one, and in the image 2 I want to take different, like the second subject right eye. I want to take here, let's take this one, right eye. So these are the images of two different individuals. Let's see the templates. So in this case you can see Hamming distance is somewhat more than 0.2 and the templates are not from the same eye. So now let's head back to the presentation for the final summary and the conclusion. So in the evaluation part, recognition rate while using Hamming distance classifier for matching two templates observed to be 90.20%, and it could be enhanced to more than 90% if you use a whole database rather than using bunch of subjects iris images. And the feature extraction and reported time using this Hamming distance approach in the matching stage was observed to be 45.76 milliseconds, which is good enough. And here you can see Hamming distance varies according to the different images type. So if you are, let's say if you are taking a bitmap image, then it might take this amount of time, and the Hamming distance will be this. And in the HUF type images, you will have these parameters. In the JPEG, you'll have these. One another interesting observation that has been made while doing this study is that FRR, which is false rejection rate, decreased when the Hamming distance is increased, whereas FAR, which is false acceptance rate, is increased when the Hamming distance value is increased. So you might wonder what FRR and FAR means. So basically FRR is the fraction of the number of rejected client patterns divided by the total number of client patterns, and FAR means fraction of number of accepted client patterns divided by total number of client patterns. So basically, if you have the, let's say if you have the threshold of Hamming distance more than 0.4, then you'll have lot of people would be able to recognize their iris patterns more efficiently. As in my case, you can see the minimum threshold which was computed was just 0.2, because of which even if the iris images are similar, but somehow their Hamming distance computed to be somewhere more than 0.2, then it will be the result that these iris images are from the different individual. So to increase the acceptance rate, we need to have the high threshold for Hamming distance in order to increase the false acceptance rate. So that's what this thing was about. So as this is mentioned, with a separation point of 0.35 as the minimum threshold for Hamming distance, these FAR and FRR were computed as FAR was 85% and FRR was 95%. So these are the curve for the Casio database, and here you can see the different percentage of FAR and FRR according to the Hamming distance. So you see, if you increase the Hamming distance, which is the minimum threshold, while comparing two templates, FAR increase a bit, but then it starts decreasing. However, on the other side, FRR decreases and FAR increases as you increase the Hamming distance. So another observation is iris recognition system can be significantly improved by testing the algorithm with more realistic data. In the conclusion part, the uniqueness of the iris pattern was determined by comparing templates and examining the interclass distribution of Hamming distance. This is the curve for interclass distribution of Hamming distance. Normalization process was not able to perfectly reconstruct the same pattern from the image with varying amount of pupil dilation, and because of the rotational inconsistency that might be in your iris images. Normalization and segmentation are the very crucial part of this model. And the normalized iris region is filtered using log-Gabor wavelets, which, unlike normalization, produces the same iris characteristics for a particular iris image under varying conditions, just like pupil dilation, different pupil dilation, and different rotational or transitional inconsistency might occur. While using Hamming distance approach for matching the templates, minimum threshold may differ depending upon the clarity of the images and pixel intensity. So that is what I just mentioned. In my case, it was 0.2, and so it's totally dependent on how your images are taken. So if they are ultra clear, they are very good in quality, then you will have the good threshold of Hamming distance, and correspondingly your FAR, which is false acceptance rate, would be more. And in the research paper given by John Dogman, we also found that only 20 data points were captured along the 240 radial lines that were drawn out from the center of the pupil. So while you do your normalization, only 20 data points were put into consideration for normalization process. So if you want to further improve the normalization algorithm, higher number of data points should be taken under consideration. Thank you for your time. For more information, you can check out my research paper, and for the complete project you can check out on my GitHub link. Thank you.